So welcome to today's Accendo Reliability webinar series or event. We're dealing with small samples, and there was a question from about 2 months ago, as I typically do, as I asked what topics would you be interested in? And somebody said, how do you deal with when you don't get enough samples? It was kind of a summary of what was requested. And I'm like, that's a good question. And it's one that plagues many of us a lot. And so let's dive into it. And hopefully my computer doesn't restart. There we go. So you've been in this situation. You're setting up a test or an experiment, or you're developing a reliability plan, or you're working with the team to figure out, answer some questions. And you realize that due to the statistics and the complexity and the all the various math we do doing conventional statistics, we need 100 samples. It might be 600 samples. I've run into some medical devices that they're regularly producing and testing hundreds and hundreds and hundreds of samples for their particular purpose. Yet you also know that when you ask for 100, you get 3 or something like that. The prototypes in particular are really expensive. And I remember working with Hewlett Packard, and when I was an engineer there on inkjet printers. And so the inkjet printer you can buy at a box store for a couple $100 as a prototype might cost a couple $1,000 easily, and the earlier ones even more so. So when I asked for 100 samples, it was significant in the budget of the process that we had. And there were software people looking for it, other engineers looking for stuff, sales and marketing looking for samples. So there was about a lot of competition for what typically was a scarce resource. And so I kind of played the game and asked for more than I really needed and received less than I really had to have and dealt with it. And so some of what I'm going to talk about today is, well, what can we do about that if you've ever been in one of these circumstances? All right. And then when then I get those 3 samples, they say, oh, don't break those. We got to put them out as sales demos or something like that afterwards. It's like, well, this really puts a hamstring on what all the fun I wanted to do with these samples. So the idea is, are you in a similar circumstance? Does this sound something like what you've run into on one or more occasions? And in some cases, like I shouldn't bring up Boeing at this particular time, not knowing how many samples they tested for that door plug that fell out of an airplane the other day. But they don't typically get a lot of fully built aircraft as samples. And the rockets, for example, full-size rockets, they're not testing hundreds of those. They might have different scenarios or ways they're doing things, but we've seen a lot of rockets blow up over the last 10 years as parts of prototypes, and they'd learn something, and then they go a little further and then they blow up again and they learn something else. Yet we're not all working on rockets. We're not all out working on aircraft. So it's a couple of people are saying, yeah, dealing with sparse samples is something that we do. And I imagine that's a very common problem. At least it has been with lots of the clients I've worked with over the years. So what do you do? And I'm going to back up that it starts long before you pull out your calculator or pencil or software packages to figure out what your sample size calculations are. So if you wanted to do I always use the 90% reliable with 90% confidence, because I remember the math for that. If I do 0 failure testing and it's just based on a pass or fail, it's binomial, I need 22 samples just to do some confidence that I'm at least 90% reliable. And there's so many times when I don't get 20 samples to do any of this stuff. And yeah, and Michael's going, yeah, I had never had enough samples. Yeah. Yeah, then you want a full analysis when you have a failure and you don't have anything left to work on. I've had that where the sample itself destroyed itself and it made it really hard to actually blew the component right off the board and melted it. Um, it's not a lot we can do with that. And so part of the approach or the strategy that I advocate, and you've heard similar things in previous webinars in creating a reliability plan, is you need to focus on what is that sample supposed to be for? What is it helping to inform? In the process of developing a product or setting up a production line or working with a new vendor for some equipment or whatever it is, at some point, we as a team need to make decisions. Is this going to work for our application? Is this going to work for our customers? And at some point, I often use the one at the last checkpoint before we go to full production and start shipping it is this thing reliable? Now we can answer that question many different ways. And it really is contingent on how important is that decision. So if we're making a minor modification to an existing or long-standing, very robust, very reliable product, that decision may be not near as important as other things as to can we expand this market? Is this product going to remain robust if we go to a new environment? Or it could be do the new vendor setup and configuration of our production line, will it maintain our stability and our ability to create this thing? Those decisions may be more important than is it reliable. Cost reductions often lead to questions like that. Yet we need to know, what are those key decisions? What is it that we need to focus on to answer well? And if it's the $1 million decision, do we ship this or not, or do we delay it? Or is it vendor A, vendor B kind of key decision, or new production facility, or new invention of some sort, or whatever? Somewhere along the line, we're going to have information to make the right decision. And so the focus really is on that first step in our job is, what are we trying to achieve? What's our goal and what's the direction we're going with? What are we trying to make happen? And what are the major decisions that are material to the production or to the process that we have for creating this product or system? And that involves talking to program managers and directors of engineering and principal engineers and people all through the team as to basically what's keeping them up at night and what's important, what's critical, and what's routine that we may not even use the information for. And so the basic gist of this is that, samples are expensive and they're sparse, that we just rarely get enough. So if you have an algorithm or a process to focus on, well, what information do I need to create that will inform the key decisions that help us make the right decision and not make mistakes, so vendor A, vendor B might have a difference in price, yet they may have very different reliability performance. Instead of just looking at a data sheet and it's such a major decision for our product, let's go do that experiment to understand which is more reliable for our particular application. And let's put samples there. And let's not put samples in the standing set of tests that nobody ever looks at the results of. It's that kind of argument is, if this is important, then it's worth investing in to get the information. It's not good to do. It's not nice to do. It's not based on anything else other than, if you really want this information to this criteria, to this type of resolution, to this type of precision, to this amount of certainty, that'll take 100 samples. And then the negotiations start. Yet you're in a much firmer setting than, here's a plan, it's a good thing to do, we're not sure how we're going to use it, and I need 100 samples. Now, hopefully you see the difference with that. And so the idea is that if we have that prioritized list of what's the most important types of information that we need samples to create the information from, then it provides a way for us to do that allocation. And there are samples that will create the essential information we need, whether it's an accelerated test or environmental test, a comparison of vendors, whatever it might be, it's linked to what's important. Now that 18th test down the line that's going to take 5 samples and it's equivalent to throw it in the chamber and see what happens. What's your history? What's your background? What's your prior experience with running that test? Have you ever found anything useful? And if it's a 1 in 1,000 chance that you'll find something useful, my argument is let's not do that unless you get the high priority ones get funded with plenty of samples, and the lower middle range sample ones meet that threshold that it's worth investing in. If somebody is not willing to send you the budget to get those samples and run that test, it's probably not worth doing. And so take those samples that I have the least interest in them, or the lack of funding for them specifically, and move those samples to the ones that are most important. Now that may sound simple, it's not by any means. The idea is that we need to do the homework of understanding what's important, that only samples can create that information for us. Now I'll talk about alternate ways of doing this as we go forward. Now, one thing I wanted to mention when I sent out the advertising for this is Bill wrote back to me and saying, hey, I'm really interested in small samples and how do you deal with that and stuff. And he sent me a handful of papers that were dealing with how do you analyze data when you have small numbers of samples involved. So if we run an accelerated test, but you didn't have the 20 samples that you really wanted, well, what do you do? How do you deal with that? And he was talking about a lot of work that he's doing and a handful of others are doing on Bayesian statistics, is using your history, your information that you have available to you as a way to analyze those results and get as much information from them as possible. Now, I'm not going to talk about analyzing it when you have very few samples so much in this presentation, but I wanted to mention it before I forget about it. Let's see. So the idea, and I've mentioned, is really this allocation idea is in the reliability planning process. And this is one of my pet peeves, by the way. I should back up a little bit. Is reliability is not just testing. It's now a lot of us have test labs, and it's a big chunk of what we do in the reliability group between vendor approval, competitive teardowns, comparative accelerated tests, new technology, characterization. We can do all kinds of experiments. One of the worst things, though, is like I've seen firsthand, is this laptop group was receiving a HALT test results and completely dismissed them. And the common refrain is, well, of course it broke. You overstressed it. And what was amazing to me, it was rejected out of hand. And they were complaining that they were required to send these samples there. I think it was 2 or 4 samples down to the test lab. And they would write this beautiful report with all kinds of beautiful pictures and recommendations and findings and so on, that in hindsight, looking at their field data and looking at the HALT reports, is like 90% of the issues that were in the field, they had identified relatively early in the development process. Yet the development team just ignored it. So there was 2 solutions to that. Help the design team understand how valuable those insights were early in the development process when they could do something about it, or stop doing HALT testing. if that team was just never going to go and listen to this stuff or make any changes based on test results, then why are you testing? Vice versa, if they understand the value of those results and it makes a difference in how they actually reduce warranty or improve customer satisfaction, then that may be critically important to them, and they will, beat on the door to get their halt test done and get the results. The difference is that we should only be using those scarce resources for those things that are most important. And important is that it's required or requested, things that we just got to do. Yet, if it's connected to those major decisions, if it's connected to what really needs to be created, what kind of information do we actually need to create, then that's where we should focus on, right? So that doesn't solve having scarce samples, but it gives us a stronger footing to request enough samples to inform the most important decisions. So that's the basic overarching number one thing I recommend is make sure that when you request a sample, it's tied to something important and tied to something that only samples can create that information for. And it's part of an ongoing discussion and dialogue that goes back and forth between you and whoever's handling the allocation or how many samples we're going to create. And that could be budget, it could be timelines, it could be all kinds of reasons what limits the number of samples we have. Yet, if you make the argument on a solid footing that this is how it creates information to inform this large, important discussion, you're in a lot better shape than just asking for 20 samples or whatever the number is. Yeah, Carl's mentioning communication is important. And I think that's the summary of what I'm talking about is if you do the reliability plan or the test plan correctly, every sample has a ability to create information to say another set of precision or another set of opportunity to find, the odd failure mechanism and so on. Each sample has an ability to create information. Sometimes more samples is the right way to go, yet why? How is that different than just throwing one in a chamber? We need to really understand the value that experiment, that information that's created, where the value is. And that's usually in informing a decision. And so it's part of understanding what's important to the people making those decisions. And that's, I think, Carl, what you're talking about is the communication part, is make sure it's back and forth in a discussion, and why one sample is just not going to be all that useful for you, but 100 samples will give you the information, not guaranteed, no experiments guaranteed, yet much more likely to generate the information that will be pivotal in making the right decision. So enough on decisions. What are some of the other practical ways we can go at this? All right. So a quick question for you, as I ranted on decisions, is how do you prioritize samples? You get however many samples you have. What's your algorithm? What's your go-to way to say, here's where we're going to go and use them? Let's take a sip of tea here real quick. I might have just scared everybody off on answering this one. I should think through my questions a little better. All right. What's next here? Some other ways to go about doing this. Now, I know many of you have experience with dealing without samples, or you just don't have enough samples. But using these things in combination with the samples you have is a very, very good way to extend the utility of this few samples you have, or just avoid using them at all altogether. Now, I know there's a couple of organizations that offer physics of failure models and simulations for circuit boards. And part of their value proposition is that the model is actually more accurate than running a test, because it'll do combined stresses, which is very difficult for us to do in many circumstances. Now, HALT gets close to some of these, yet the ability to simulate, say, thermal cycling at use conditions is much different than thermal cycling in a HALT chamber. Here we have internal temperature variations that are very subtle, yet over time, those cycles can break vias and break solder joints and things like that. Now we being the reliability industry has pretty decent models for thermal cycling damage to solder joints, for example, and all kinds of other issues, whether it's vibration or electrolytic capacitor degradation or LED degradation and so on. And there's dozens and dozens of models in these different systems. Yeah, and Maximilian, good question. I mean, the two that I know of are out of Kels, and I'm drawing a blank on the name of their thing, and then DFR Solutions, which got bought by Ansys. I think their software is still available. Those are the two big ones for that I know of for circuit boards and circuit assemblies, and I'm sure there's others out there. Yet, even if it's just a paper that's on a particular mechanism that you and the team is like, yeah, this is important. We need to understand this. The physics of failure modeling systems and papers and doing it by hand can really give you insights that you may not otherwise get. The trouble I've always had with these models is they do require quite a bit of information to populate them. They're getting better. A lot of these software packages are, giving you, here's the likely options for if it's this kind of stack up of circuit board, here's the modulus for that particular material and so on. You don't have to look up all of these different features yourself. But the idea is that there are models and history and previous papers and literature that talks about how things fail. And if we're looking for how, say, solder joints crack or how vibration will affect our circuit board or whatever, there's probably a model out there. And getting comfortable with using those allows us to avoid, in many cases, using samples. Now, for very important things, you might use the modeling and simulations and emulators and things like that to get a pretty decent idea of what the direction is, and then use just a handful of samples to verify those results. And I think of the wing testing that's done with major aircraft carriers is they'll build out a wing and they'll bend it until it fails. And they have plenty of models that say it should fail at so much force, so much deflection. This is where and how it should fail. And if it is less than expected, then they know their models are wrong and they're back to the drawing board. If it's more robust than they have, well, they over-designed it, and now they need to either keep that or figure out how to back it off. But either way, their model's not right. Now, as you know, I think it was Cox or Box, one of those guys, the statistician said, all models are wrong and some are useful, or there's something to that effect. But the idea is that using existing information is a great way to, one, if you have to use samples or run an experiment, these models actually give you a really good clue of how to set up those tests and what you're looking for. Now, on the screen, there's a bunch of other ones: expert judgment, computational fluid dynamics, all those other things, simulations. It was George Box. Thanks, Scott. The idea is that we have lots of other approaches, everything from engineering judgment or expert judgment, and there's a variety of ways to go about making the most of that information, but also finite element analysis. One of the things I've run into over time is that the mechanical engineering CAD systems are getting really good at running, and many of them have decent finite element modules in them, even to the point where they can do drop testing and simulate it and get a lot of information about where the forces are going if it hits this particular corner, for example, from a certain height. We can very quickly run these simulations or analysis and get insights that then allow us to do a much smaller set of experiments, much in order to verify it. If we're looking at how does drop testing work for our particular product, and we do 10 drops and all the faces and corners and edges or stuff like that, we may end up destroying a bunch of samples or creating a lot of damage. And we may likely never really understand where those forces are coming or how much force is there or what kind of mechanical structure is amplifying the impact that's happening or dampening it. Whereas the modeling systems allow us to go slow motion and really get a good picture of what's happening when it hits this particular edge. And in finite element, we can drop it hundreds of times at different orientations and learn a whole lot much quicker than going to the lab. And so it's using these kinds of tools that we, as the reliability people, may not be the experts at it. Yet it doesn't take much to convince somebody, do you want to spend $250,000 on a handful of samples and maybe not get anything useful? Or how about we spend a couple of days using this tool that you have called finite element or some other system and analyze it so that we can get the most out of the very few samples we have or get insights that may prevent us from having a bad design right from the start. One of the things I've always encouraged the mechanical folks to do is, well, what happens when your material gets a little bit older? What are the chemical changes, the set, the degradation due to UV radiation, the temperature cycling and crack propagation? How is that going to affect the strength and structure of your system? You can build that into the design and then run the analysis to see if it's different than when it's brand new. And or what's the variation of steel strength? Let's run it such that we look at it when it's stiffest or it's not it's more pliable. What does that do to the performance of your process? And those things, yeah, they still have a cost, yet they're nowhere near that extra sample that we just can't get. The other way to go about this is, we actually know a lot of stuff already, and it builds into our expert judgment in many ways. And part of it is that if you've got an existing set of products out there, it's a pretty good bet that major elements of that product are similar to or the same as the product that you're working on today. It's rare that we start off from scratch, from dead zero. And so the field data, if we pay attention to it and make efforts to actually get decent field data and failure analysis of things that are going on there, same with prior testing. If we do good basic engineering, is keeping good notes and finding out what we know and don't know and keeping track of it, we end up with a pretty good database of useful information to inform future decisions without going back to the lab to do testing. And so the history that we have is oftentimes our best place to look for information, right? And I'm going to save vendors for way later because your mileage may vary. The other way to think about this is, do I need the whole system? If I really need to perform some testing because it's important for the power supply submodule of our system, it may be a whole lot easier to get 100 power supplies than it is to get 100 full systems. Now, you might need an emulator to load it or some other way to simulate the load that power supply would get. Yet 9 times out of 10, that's a whole lot easier to accomplish than getting full systems. And same with components. If you're having trouble with the electrolytic capacitors, you can get a reel of 10,000 of them pretty cheap, probably cheaper than any sample of your full system. You might have limits on just how your test setup or size of your chamber, things like that when you're dealing with components. But I've also done, if I'm interested in how do different chemicals and day-to-day materials that will come in contact with our system, say it's a phone, and then you want to know if lipstick or perfume or sunscreen or cleaning solutions or whatever, how does that affect the finish of our system, of the polymer parts usually, or maybe the coatings that are on it? There's actually a formula out there for artificial sweat. Make sure you refrigerate it and throw it away as soon as it starts getting stinky, is the way I say it. But anyway, we can do all kinds of cool chemical stuff on things, but do you really need a full system to do that? Can you replicate the coatings and material finish and paints and everything else in a way that replicates, say, the thicknesses or application process on a coupon, on a panel, on just a mock-up? You know, do we really need the circuit board behind that panel? And if it's creating a bunch of heat, well, let's put a heat gun behind it or a heater. Let's make it simple so that we can get the samples we need to run these tests. And it's one I've run into a rare, you know, on occasion, but not too often, is that we always test full samples. All right. Well, if you can afford it, go for it. You're wasting a lot of material and time here, but that's just me. Let's see, a couple of comments coming in here. Let's see. Either Q model, Carl, you're in the questions tab. I don't know what a Q model is, or template. A question model, maybe. Detailed guidelines. If you're referring to, you know, building the reliability plan and going after what's important, what are the key decisions, that's in the book that Carl and I did. And I'm thinking, I've drawn a blank of what chapter it is, but the idea is that, yeah, there's a lot of questions that we've set up as is not guidelines or checklist or anything like that. Very purposely saying, these are the types of things to think of, and your circumstance will create a different list. But when you go talk to program managers or key engineers or people that are working on making major decisions with your product, the essence is what are they worried about? What is the thing that they really want to get right? All right, now put your money where your mouth is. How much are you going to invest in to get the right sufficient information so you can make the right decision? So that's part of what I'm going after, is when you are trying to question people or understand what the high performance or high priority things are. All right, so I'm trying to illustrate there's a good number of other ways other than with samples that we can get the information we need to inform decisions. All right. Books, papers, and I really strongly urge you not to use Mill Handbook 217 and similar tabulated failure rates. They are often, in my experience, less than useful. So do your due diligence, get the distributions, get the insights you need to understand the failure mechanisms that you're trying to explore. Is this going to apply in your case or not? Now, on the other hand, if you're trying to do something that's, you know, I think I talk about it coming up, but if you really only have a handful of samples, what can you do with that? And so we'll talk about that in the next segment. Some vendors actually publish white papers and have great information about the accelerated testing they did. And here's the variables. And here's, if you're using it and I'm thinking of a IGBT, it's a device that changes DC power to AC power, for example. And they're used in inverters. They're in electric cars, they're in solar panel or solar systems, stuff like that. If you're using it in say a solar field where it gets turned on and turned off once a day and it's converting to 60 hertz, it has this type of expected failure mechanism. And here's the accelerated test for your particular circumstance, your temperatures, frequency use, and so on. And you have a pretty decent model right there on the vendor's site. And then vice versa, if you're using it in a high switching, like very high frequencies, then that same component could be used in a different way, and it has a different failure mechanism. And they have a separate paper for that. And here's the models, and here's how to use it, and so on. It was amazing. It's rare that you find a vendor talking about failure so clearly. Some do if you get an NDA in place and can talk to them and do it. But a lot of us don't have the time to track down every vendor and try to track this information out. But I found that it's useful to at least ask. Now, one thing that I've heard is a hurdle to this is that we don't buy enough from them to be a big purchaser, so they don't listen to us. I argue that that's not necessarily true. The margin on the parts you buy are higher than the ones that the big companies buy because they can negotiate it down. So they make more money per part than you do. You're also willing to share with them information about how you're using it, which is something many vendors just don't get. And you're looking at, well, how do I best use your product? Which gives them insights how to improve their product. Don't forget, you add a lot of value when you approach a vendor looking for how to understand their product and its application in your situation. They don't have that information otherwise. Or they hallucinate it. I guess ask ChatGPT to come up with a use case for them or something like that. I digress. Failure labs. If you've got a good relationship with your internal or external failure analysis lab, and you have a component that you're concerned about, well, what do they know? They might have models, they may have data, they might have analytical information that says, oh, and one real case I ran into is we're seeing a lot of failures with vendor A over here for this same component that vendor B makes. We never see their products in here, and our customers are using both. So it's anecdotal data, information. We don't know how many were installed. We don't know everything else. Yet we've got a bit of information there to look for a particular failure mechanism in one versus the other, for example. And the last one, sometimes it's actually easier to get your competitor's product than it is to get your own samples. We can learn a lot by taking apart a competitor's product. Why did they go to that solution? What difference in their engineering thought process led them to that solution? That can be used to inform decisions also. So lots of different approaches, from physics of failure modeling to finite element analysis to history, historical data, failure analysis labs, and so on. There's lots of other avenues for us to gather information that can either supplement or replace the information created from samples. So I'm hopefully helping you understand that we can take the pressure off of how many samples we actually need. Okay. Now, of course, there are some experiments and tests and so on that you just have to have a sample for. There's not a other viable way for us to get that information. So we need samples in some cases, in many cases. So let's take a look at some of those. And I gave a quick story there about great vendor information. It was just something I was looking on their site. How reliable is your product? How does it fail? The typical questions I asked vendors, and I ran across it. They didn't offer it. Our procurement team didn't have any idea about it. They never asked those questions. So it was a nice find, and I've made it a habit to look for that kind of information, ask for it with every vendor I work with. All right. So how do we get the most out of the samples we end up getting? What can we do to do that? So part of this process is, and it's one technique I ran into years ago, was called a waterfall test plan. And I don't really understand what that is, and we didn't take long to understand it. Let's say you have 10 samples and you have a whole pile of environmental tests. Well, there's two bits of logic to this. One is, what's the most benign? What's our engineering judgment and history tell us is the easiest test that we are doing because we're worried about this, that, or the other thing. Yet we think it's a low risk for our product. And it might be that we're going to run, we have all these different use cases and scenarios, and some are like an inkjet printer. It's set up in a home and it's used occasionally. Turns out that's actually leads to a whole raft of unique failure mechanisms that are completely different than if you use your printer quite often, like every day, all day long, which leads to different problems. But so you want to check it, yet the collateral damage of those stresses is not going to prevent that same sample from being used for some other type of testing. Or part of the logic is that I really don't want to put a dust chamber inside my thermal cycling chamber. One, it's messy. Two, it probably will destroy one or the other of those two test beds or test devices. But testing a perfectly clean, brand new product may not lead to issues that I'm interested in, because we are going to be using this product in a dusty environment. So let's run the dust first, see if there's any big issues on it. But the collateral damage that occurs from that, or the conditioning is another way of thinking of it, that occurs, can be emphasized or used later if I do thermal cycling. So if I have a little bit of dust in something, or if I get a little bit of moisture in a product and I do freeze thaw cycles with some thermal cycling on it, those particles or those ice crystals can cause leverage to break things. Whereas if I ran a pristine, right off the production line product in that thermal cycling or freeze thaw test, there's not that collateral stuff there to cause problems. So think through how you can layer stresses in a meaningful way, either by what's not going to destroy my product, but what's going to coat it with a set of stresses that we can carry into a future test. Now, Carl's got a website for it, a waterfall test plan. Cool. Yeah, and David, you're ahead of me on this one. I think it's on my next slide. Yeah, and Michael, you're exactly right. Vendor data is sometimes just advertising. Yeah, definitely. You got to sometimes ask questions and dig a bit deeper and try to find somebody other than the sales guy to help you. But compliance testing, I'm talking about that. I believe it's on the next slide. Or regulatory is another one to do it. But waterfall's a way to go about doing this and to get the most out of your samples. And so you might get deeper into that pool of things, of those decisions that we're focusing on that are more marginal. You know, it may not be worth getting 10 samples just for dust testing. Yet, if I can incorporate that into another sequence of testing, that added dust may be very useful for us to understand how it's being used in an actual environment for a major decision, maybe a major design decision of what kind of casing we're going to use on it, then, or seals we're going to use on it, then having that dust test as a precursor to, is the seal integrity good enough or not? You have to think through it for your particular circumstance, but the idea is that you can use these samples in multiple ways. Now, worst case is that your most benign, easiest task destroys it. Well, then you learned a lot. It's not all that robust, is it? But if you add thermal cycling, and then you add dust, and then you add water ingress, and then you do a freeze thaw test, and then you do something else, you're increasing the amount of stresses and chance of failure that are occurring. And it's not quite a halt test. It's think through what's the sequence of how your customers are using the product and what kind of environment they're in, and how does that set of conditioning affect your ability to say, will it last 5 years, for example? So if I simply throw it in a chamber for high temperature and assume that it's a Arrhenius equation, I'm probably missing a huge number of failure mechanisms that may or may not be really relevant for us. And so thinking through how you prepare your samples and compare and contrast them may become critical to how well you use each and every sample that you have. Right? Another method or approach or strategy is use test methods or approaches or strategies that just inherently use fewer samples. Now, I mentioned Bayesian analysis earlier, and I don't fully understand Bayesian analysis in how you do data analysis using those techniques and so on. It's not something I've spent a whole lot of time on, so I'm very clear that yeah, I know it's out there and there's people that are good at it. And when it seems like it's the right approach, I go talk to them. The idea, though, is that even in test planning, if you can incorporate your prior information, your history, the background, the stuff that you know, in order to inform, say, sample size calculations, you could reduce the number of samples you need for a particular circumstance. I've not found it to be all that terribly useful, but that's just me and my limited, very limited experience. But HALT typically only takes 2 to 4 samples. It depends on what book you're reading. And you can get a lot of information out of it. Now, the danger is that, well, what if you don't need that information? Nobody is really looking for what's the Pareto of likely failure mechanisms, because in some circumstances, we already know. We have historical data and we're trying to make improvements on it. And we have a long list of things that need improving. Well, HALT will likely just replicate much of that. Now, there are arguments that doing repetitive halts on samples as you make improvements helps you understand if those improvements are there or not. And that's a strategy. But using HALT in that kind of method is appropriate in my mind. But if you already know what you need to go solve, and using a tool to go discover where the weaknesses are, it loses its allure, at least to me. If the results of doing a HALT are compatible with informing the decisions that we need to make, the high priority decisions, then I'll by all means use it. But it also might be a trade-off. Instead of understanding if it will last for 20 years and under these sets of conditions, we can do HALT and say, well, here's the likely failure mechanisms that will limit the life. That is a slightly different approach, a different view, a different perspective at answering that question. And we won't be able to say, yes, it will last that long. We may be able to find mechanisms that we have good models for, and we can do some calculations. Yet you might not be able to fully inform the decision by going to an alternate tool that uses fewer samples, or you get lucky and have really good information. The other one is comparisons. This one's often overlooked. I don't need as many samples to understand the difference between vendor A and vendor B's performance in some degradation or some, say, crack propagation or whatever it might be. I may be able to do a test just to understand which is better, which is more robust for a particular circumstance, as opposed to understanding, will each of these last for 20 years under a range of different stresses? So comparisons, detecting a difference is sometimes, not always, but sometimes a pretty efficient way to use samples. And I'm sure there's others out there, and I will leave that to the chat to, if you come up with some of these other tests that really limit how many samples you have. I'm trying to, I just had another one, a good example on my tip of my tongue, and I lost it. But yeah, that's not the only way to get the most out of your samples. Here's another way. And this is, I think it was Michael that foreshadowed this one, is Oftentimes a product needs to go through regulatory testing or compliance testing, and sometimes for multiple jurisdictions. And so we end up allocating samples for electrical surety, or is it fail safe when it's supposed to, all those kinds of things. Sometimes those tests are pretty benign. They're not, oftentimes they're not destructive. And now we have the sample left over that just saw, say, instead of 120 volts, it saw 200 volts. Okay, well, power supply failed, but I can replace that and I get the rest of the sample. Or I learned something about the power supply. But the idea is that the software folks need samples to run their software and make sure it's doing what it's supposed to do, and the green light comes on when it's supposed to come on. Not some of my friends are software engineers, but when I say stuff like that, I probably lose a few. The other idea is that the engineering team gets samples, the sales team oftentimes gets samples, marketing gets a sample or two, software gets a pile of them, regulatory gets a bunch. They all have to be turned on. They all, get their run through the paces. Do they do what they're supposed to do? If we can gather that information, that's just that information. Did these samples work? Gives us information about out-of-box failures or, initial failures. Yeah, these are prototypes and there might be issues with the prototyping process, but what about that one that's like, oh, it doesn't work at 240 volts? That's actually very, very useful information. And we didn't even have to set up and run the test. These kinds of use of samples are not our samples. They're the ones that were allocated to the others. Yet it doesn't take much to organize and gather and help the rest of the organization understand how important it is that their observations, that their hurdles to get what they need from the sample to work is critical information for the reliability team. And so it takes time to get people to actually spend a moment to say, hey, this handle fell off when I pulled up on it, but I'm a software guy. I don't care about the handle. They understanding that and seeing it is a way to extract information on samples you don't even own. It does take a little bit of effort and sometimes cajoling and changing the process. But the idea is that if we make 100 samples total and I only get 3, well, what about those other 97? What can I learn from them? Now, it may or may not lead to the perfect information for your most important decisions, yet they start filling in the gaps for those things that we were prioritizing our samples away from. So we can go a little deeper in that list of things that samples would be useful for. Maximilian is asking, do I have a favorite method or tool to track the issues, observations, and so on? Many organizations already have a defect tracking system of some sort, a bug tracker. Sometimes there's 2 of them, one for the software team and one for everybody else. I ran into one organization, had 6 different systems, and they had a full-time person translating them from one system to the other so they got to the right place. Even a chalkboard, if you have a small team, chalkboard, now I'm dating myself, a whiteboard or even a piece of paper or just somewhere the organization can say, all right, what do we observe or learn this week? What's important for us to learn more about and do the failure analysis on? Which ones lead to design changes or process changes? A FRACIS system is what I'm talking about, failure reporting and corrective action system. And I think I have 1 or 2 webinars on just that topic, of some that have gone horribly wrong, and others that are really, really useful. But the idea is that it's more the culture. If the rest of the organization understands that, hey, I opened this and the hinge fell off, or the screw was found on the bottom of the case, those simple observations are ignored if they're looking for, hey, did my software do the right thing, or where do I plug in my emulator, or load type devices or whatever, or for what they want to do with their samples. If they understand that beyond their own experiments, their observations of the performance of the product in all the fields of engineering are important, and they can lead to insights that we would otherwise not have. Now, this one's more of a cultural thing. We're all pretty busy, and I don't have time to go write a report for what I got. And then especially if you, then the system says, oh, you found it, you fix it, kind of an attitude. And that might work in a startup. Yet most organizations where we're siloed a bit, that's just not going to happen. You'll stifle anybody reporting these things. So it's the old axiom of what's in it for them kind of idea. If they understand that if we can fix these issues, we all win. We get, one, we get better samples the next time around. Two is we get samples that actually work. Three is that our customers are happier. And hopefully that's a priority in across the organization. So hopefully that outlines a great many different way to get the most out of samples, to get, first, make the argument to get enough samples for the critical things that that organization really wants to know. And samples and test samples is the right way to do it. Two, don't use test samples. Simulations and emulations and models and historical data, vendor data, all kinds of other tools and techniques exist out there that doesn't need a sample. Let's explore that wide range of things. And will those methods provide sufficient information to inform those important decisions? And then third, if you've got samples, get the most you can from them. Use them as cleverly as you can to extract all of the information you can to inform as many decisions as you can. And don't forget all the other samples that you did not get allocated. You can look over other people's shoulders to say, hey, is it working? Is it doing what it's supposed to do? Have you noticed anything? That's fair game in my book. And then the Fracas system is a great way if it's used and implemented well, and that's beyond the scope of the few minutes I've got right here. If you're really interested in that, Maximilian, let me know, and I'll see if I can track down which video that was. I think it was on Golden Nuggets, might be been one of them. But I know I've talked about Fracas before. All right. So I've only once ever had more samples than I needed. And that was with zip ties, the little plastic ties that you use to attach a cable to a frame, for example. And this was with a solar field. And they had 3 different vendors, and they wanted to know which zip tie would survive the environment that they're putting these things in the longest. And so it was an accelerated test, and we were aging them in different ways. And one of the tests was a tensile strength. And we only had one Instron machine and one tech that could do it. So we were limited, not by how many samples I had, but by how we measured it. And so we ended up only testing, I don't know, like 500 or 600 of these things. Yet I had boxes of these. I had thousands of samples, which is really nice. But if you can't test it, then you get limited a different way if you can't evaluate it. So I've only had that happen once. It was a revelation that had ever happened. The vast majority time, 99.999 times out of 100, I don't get enough samples to do all the things that we're being requested to do, or that are deemed important to do, or we typically do, whatever. So you got to really think through asking for it and how you go about using them to get the most out of it. Okay. Anything else? I got a moment to go, and keep my fingers crossed that my computer didn't restart this time. I don't know if it's the restart before I opened up the room, closing all the other applications, all the other stuff, but hopefully something there did it, or it's an intermittent problem and it'll show up next week. I just won't know. But anyway, good turnout. I guess sample size is a great topic. If there's other questions or other elements to this or pieces of this you'd like to dive more into, let me know. Give me a shout out, an email, or a comment here. I'm always looking for what's on your mind, what questions you have, what can we do? It's we're in this to learn. I'm pulling on my experience and a lot of conversations with folks like you. So I want to mention that. See, Mahindra's bringing up, a couple of comments bouncing around there. Let me open this up. With limited samples, any kind of lifetime testing is nearly impossible. I agree with that. With reasonable timelines, typically focus on design margin. Yeah, focusing on creating a good, robust product kind of precludes the need to do a lot of, is this good enough? Is if you've designed in a lot of robustness and redundancy, for example, things like that, yeah, it's not as important anymore. Change what's important is it by the design practices. That's a good thing. Any sources or to reference material when needed to conduct an analysis with full samples. Jason, Bill Meeker, William Meeker, I think it's William Q. Meeker, is his book, and I can see it on my bookcase here. I think it's Statistical Methods or something like that. It's Reliability Statistics by Meeker and Escobar in the first one. I think they added a third author for the second edition of it. And he has a couple of chapters about dealing with small samples. And he's got new work coming out that's talking about using Bayesian approaches to do the analysis. So there's a couple of pieces there. Hopefully that gives you a deal. If not, if you don't find anything, Jason, let me know, and I'll introduce you to Bill so you can maybe point you in the right direction for what you're trying to do. But things in my mind is the Bayesian analysis is one way. Another is a bootstrap. It's a way to take the results of sparse number of samples or elements in your experiment and get really good estimates of the actual variation, the variance terms, which really helps you in making decisions based on small samples. So instead of using a, say, sample of 10, Bayesian or bootstrap method will give you a much tighter estimate, closer to the actual value than using the traditional methods we use, where you're dividing by n-1, and it ends up being a very large, a relatively small number. So the division makes the results really expand. So a couple different ways to look at it. But yeah, let me know. And if you can't find stuff by Meeker and his team on analyzing sparse sample results, then I can hopefully get you to the right people to find what you're looking for. All right, we're about a minute or so off. People are heading off to the rest of their day. All right, appreciate it, everybody showing up. And then again, if you have any thoughts or ideas for future webinars or anything on your mind, just let us know. Always interested in, and really appreciate the turnout today and all the interaction of it. Much appreciated.